Okay, so I want to talk about the derivative of the sine function. This is going to be a precursor to talking about the derivatives of all of the trig functions. And the first thing we're going to do is just kind of explore the derivative of the sine function using its graph in the same way that we have looked at how we can estimate or sketch a graph of a derivative of a function from the graph of an original function. So think for a minute about what a sine graph looks like. Hopefully, in your head, it looks like this. Okay, there's the sine graph. And remember what we have, like features of the sine graph is it is periodic with period 2 pi. So here is one full period. Okay, and that's 2 pi units. And then that repeats. We also know that the range of the sine function goes from -1 to 1. It's an odd function, so let me write these things up. So periodic with period 2 pi. The range is from -1 to 1, and it is an odd function. I guess that's sort of the main crux of things, features that we want to keep track of. We're going to try to sketch a graph of this function. And in order to do so, I'm going to label my key points in the x-axis. So let's do that. And so we have kind of key points every pi/2 units. And in terms of looking at the derivative, one of the things we want to look at is where is the function increasing and decreasing? Where does the function have horizontal tangents or even potentially like no tangents? This is a nice smooth graph, so it is actually going to have a tangent line at every point. Another way to say this is it is going to have a derivative at every point. So let's look at the features kind of on one basic period. So one thing is we have a horizontal tangent here at pi/2. We have another horizontal tangent at 3 pi/2. It looks like we've got a horizontal tangent at all of the odd multiples of pi/2. And between those 2 points, so like say between pi/2 and 3 pi/2, we can see that the sine function is decreasing. So the derivative has to be negative in that range. And in this range from 3 pi/2 to 5 pi/2, we can see that the sine function is increasing. And so the derivative of that function has to be positive. And you can kind of see that the shape of the graph from pi/2 to 3 pi/2 is exactly the same as the shape of the graph from 3 pi/2 to 5 pi/2, except where one is increasing, the other one is decreasing, but they're increasing/decreasing at the same rates in those two different intervals, right? So like whatever the derivative is here, at this point, if I go to the same sort of portion of that interval in the next interval, then I have this point, and the derivatives of these at these two different points should actually be the same absolute value, but opposite signs, right? Because where one is increasing, the other one is decreasing, but they are increasing/decreasing at the same rate. They're because of all of the symmetry of the sine curve. Okay, so since I actually have both positive and negative derivatives here, and it looks like it's going to be symmetric positive and negative, I started to draw some axes for my derivative graph, and I'm going to go ahead and put that x-axis right in the middle to give myself equal room above and below the axis for graphing the derivative or sketching the graph of the derivative. And I'm going to go ahead and mark those pi/2 marks So here's my negative pi, negative 2 pi, pi, 2 pi, 3 pi, and 4 pi. And I'm just going to eyeball where the middle is of each of these. Okay. So the first thing I might want to actually mark is that at the odd multiples of pi over 2, this is where I have my horizontal tangents. So that means the derivative is 0. So at these places, odd multiples of pi over 2, we have horizontal tangents. So the derivative is 0, so the derivative is going to be 0 here, here, here. Okay. And I'm going to look at, let's look at the interval from negative pi over 2 to pi over 2. That's kind of a nice interval. In that interval, we have that in there, the derivative, the function itself is increasing, so the derivative must be positive. So I know the derivative has to be positive in this interval from negative pi over 2 to pi over 2, right? And it has to come down to 0 at negative pi over 2, and it's 0 at pi over 2. And if you look at, if you kind of ask yourself, like, where is the steepest part on this curve? There is so much symmetry in this graph that the steepest part must actually be in the middle, because I know that the shape of this piece here must equal the shape of the other piece, the next piece over, partly because sine is an odd function, partly just because of the definition of sine, that there has to be all of this symmetry. So that means my maximum slope must be right there in the middle. Now we can take a guess at what value that slope is, but I'm just going to mark it at some number, like I don't know what that number is. I'm just going to put it there, put a question mark, but that is the maximum value of that slope. Okay, and so then I must have some symmetry coming down to meet 0 on both sides of that. I make my derivatives in orange for some reason. Okay. Now, between pi over 2 and 3 pi over 2, the sine function is decreasing, so that means the derivative must be negative, so it has to be down here. And again, since there is so much symmetry here, the picture of this portion of the curve looks exactly like the same as the picture of the portion of the curve between negative pi over 2 and pi over 2, except it's decreasing instead of increasing. But it's decreasing at exactly the same rate that the other portion was increasing. So this picture from here has to look exactly like this picture from negative pi over 2 to pi over 2, except in the negative direction. So whatever this value is, that is the maximum slope at 0, that also must be the minimum slope at 3 pi over 2. Sorry, at pi. So it has to go like this. Okay? And then basically, we have completed one complete cycle, and so the rest of this actually has to repeat itself. The rest of the derivative function has to repeat itself. Okay? And if you ask yourself, what does this derivative function look like? I hope you are asking yourself this. And I hope you're coming up with some sort of an answer. So this is approximate graph of the derivative of sine x. So we don't know what this max and min are. We definitely can see it must be a periodic function. And if you ask, like, what period does it have? It has to be with period 2 pi again. And if I look at, sort of the one fundamental period corresponding to the fundamental period of sine from 0 to 2 pi, this looks like, it looks like this. Okay. What about the range of this function? Well, we don't actually know what the range is of this function, right? Because it depends on knowing what that maximum slope is at the steepest part of the curve. But so whatever that maximum is, that's also the opposite of that number is also the minimum value. So it is a symmetric range, even if we don't know what the actual range is. And we can also see that there is some symmetry to it. And if you take a look, we can see that it must be an even function. And this kind of goes to just looking at the symmetry of the sine function, that you must have kind of an opposite symmetry of its derivative. Now, you might be thinking, this looks an awful lot like the cosine curve. And I agree with you. It looks an awful lot like the cosine curve. And it certainly looks like it must be related to the cosine curve. In order for us to determine with confidence what the derivative is, we actually need to do some calculations with it. But before we do that, I want to actually do this sketched graph of the derivative using the precision of Desmos. Okay. So here is the sine curve. This is the graph where I can drag these points to make little segments into tangent lines. Okay. And so I'm just going to drag these points until each of these little line segments looks like it's an actual tangent line. So that looks about right. That looks pretty good. That looks like 0. Oh, that's positive. This looks like the steepest part of the curve, so there it is. Okay, that's 0, negative. Steepest part of the curve is here. Okay. Now looking at this, if I put on the grid, now looking at the values of these little orange dots, it does actually look like the maximum slope here is 1. And if I zoom in, I'm going to zoom in here and wiggle this a little bit, and it really does look like the maximum value is 1 there. Okay. And I can kind of zoom each of these points a little bit. That 0 looks right. Oh wow, that looks really good right there. Okay, that looks pretty good. It's funny that works out exactly there. Let's see, wiggle it. That looks about right. I know I'm kind of biased. I really want it to land on that 1 there. Okay, so this does look an awful lot like the cosine graph. And I am just going to go ahead and plot the cosine x graph to see, and it really does look like that is the correct graph for the derivative. Okay, so I'm going to go ahead and confirm that the derivative of sine is definitely cosine. Okay, and that is an important piece to keep in mind, and it is important to have the experience of not of actually going through the calculations. We will go through the calculations at a later date. But right now we're going to accept that the derivative of sine is cosine. Okay, we have seen some evidence based on like a very fast hand-drawn sketch of the derivative, and we saw a little bit stronger evidence based on using some technology to get a more accurate sketch of the graph of the derivative. And I'm going to, confirm for you, yes, the derivative of sine is cosine. And we're going to use that and move forward. And then in a later video, I'll actually go through the calculations of how you know that the derivative of sine is cosine. Okay? So derivative of sine is cosine. I'm going to turn this off and I'm going to close this. So if you want to look at this graph, which is should be available in the description, then each of these has sort of some pieces in it. The original function is in bold, and then the derivative is in some thin, usually orange color. And so let's actually look at this. I'm going to turn off the grid just to clean up the space of what we're looking at. Okay, so here's here's the sine graph, and then the derivative is cosine here. Okay, and we get the confirmation that the derivative of sine x is cosine x. It's just written here. It's not actually, this isn't actually graphing anything. Okay, but if I click on this, that shows the cosine curve exactly overlaying the curve, which is showing the derivative of the sine function. So thinking about, like, if the derivative of sine is cosine, what should the derivative of cosine be? If the derivative of sine is cosine, you know that the cosine curve is exactly the same as the sine curve, just shifted to the side. So that means the derivative of cosine should be another sine curve shifted somehow. If we take a look at this, so cosine is the bold green function, and then the derivative of that is the thin orange graph. And how would you, like, what curve is that? If you know that it's some sine curve, what sine curve is that? Hopefully you determined that it is negative sine of x. So the derivative of cosine is negative sine. All right. Now, the rest of the derivatives are not entirely obvious. So here is the derivative. Here's tangent. The tangent curve is the one in bold, right? And we have asymptotes at all of the odd multiples of pi over 2. That's where the tangent function is not defined. Notice that the tangent function is an always increasing function, and so its derivative is always positive, okay? And we have the tangent function is periodic with period pi, and its derivative function is also periodic with period pi. This does not look like any trig function it is not one of our basic trig functions. So we're actually going to use some tools from differentiation in order to calculate what is the derivative of the tangent function. And we can actually, let's just take a look at the derivative of secant. Secant is this one in bold, the purple, and the derivative, well, it looks kind of like something like a tangent, but the tangent always is increasing, but this is sometimes increasing and sometimes decreasing. So there's something wild going on with the derivative of secant. And of course, the derivative of cosecant should kind of be similar. And there's derivative of cotangent. Since the graph of cotangent looks similar to the graph of tangent, we're going to have kind of similar derivative pictures, okay? So I'm not going to go into those right now in the precise graphs, and I actually encourage you to not click on those arrows yet. We're going to go back and do calculations in order to figure out what the derivatives are of the other functions. Okay. So now let's actually accept in our lives that the derivative of sine is cosine, and the derivative of cosine of x, negative sine of x. I recommend that you actually take whatever means you need to memorize these, okay? One of the things that you can do is you can remember that sine and cosine are derivatives of each other in some way, and kind of keep in mind this picture that, like, you know, here's the sine function, it goes like this, and so its derivative must have, well, it is 0 here and 0 here, and it's negative in this place, and it's positive there and positive there. So you can quickly draw the picture of how the derivative of sine is cosine, and the derivative of cosine, if I draw that first, the cosine curve looks like this, and I'm going to quickly draw its derivative as a sketch. I have a horizontal tangent here and here and here. That's at 0 and pi and 2 pi. And then the derivative is negative at the beginning, so it looks like this. And the derivative is positive for the second half, so it looks like this. Okay, so then we see that negative of the sine curve. All right. Memorize the pairings, derivative of sine is cosine and derivative of cosine is negative sine. Also, be prepared in times of lack of confidence, or, you know, maybe you have some question about whether your memory is correct. Be prepared to just draw the pictures really quick to confirm for yourself that these are the right derivatives. Okay? All right. So now, how do we calculate the derivative of tangent? Well, tangent is a quotient of sine and cosine. So that tells me that the derivative of tangent of x is the derivative of that quotient. And when we calculate that derivative, we use the quotient rule. So this is going to be quotient rule. So it's going to be bottom times the derivative of the top. So cosine of x times derivative of sine x minus the top times the derivative of the bottom. So sine of x times the derivative of cosine of x all over the bottom squared. Cosine of x squared. Let's do some more calculating. So this is cosine of x times derivative of sine x is cosine of x minus sine of x times the derivative of cosine of x is negative sine of x all over cosine of x squared. All right, so this is cosine squared of x plus sine squared of x all over cosine squared of x. You have two options here. You can use a trig identity to say cosine squared of x plus sine squared of x is 1, or you can separate this into two fractions, cosine squared over cosine squared plus sine squared over cosine squared, and then deal with a trig identity after that. I am going to recognize that this cosine squared of x plus sine squared of x is equal to 1 using the Pythagorean identity. So this is 1 over cosine squared of x. And 1 over cosine of x is secant of x. So this is secant squared of x. Okay, what did we start with? This was calculating the derivative of tangent of x. So derivative of tan x is secant squared of x. And if you think about that, and does this make sense? If I look at the tangent graph, so tangent has these asymptotes at the odd multiples of pi over 2. Here's pi over 2, negative pi over 2, right? The tangent graph looks like this. Okay, secant squared of x, like secant of x looks like, it's like this, where the minimum value is 1 here, and then the maximum, the local maximum is -1. It looks kind of like this, right? This is y equals secant of x, okay? Now, if I square that function, for one thing, all of the negative values are going to be made positive when I square them. But also, my 1 squared is going to be 1. And then the numbers that are bigger than 1 are going to get slightly bigger. So secant squared is going to be like kind of like this. And then this, squaring all of these negative numbers, is going to flip them up, and I'm going to have this. Okay, so where secant is periodic with period 2 pi, when I square that, I actually get a function that is periodic with period pi. So this would be y equals secant squared of x, okay? And you can check that out in that Desmos graph. All right, that is tangent. I highly recommend that you take the time to calculate the derivative of cotangent yourself. And I am going to now calculate the derivative of secant. So the derivative of secant of x, well, secant of x is the same as 1 over cosine of x. So I can use the quotient rule, or I can use the chain rule. You might actually recall that the derivative of the reciprocal of a function, basically using either the chain rule or the quotient rule, it's the derivative of the function in the numerator and the function itself squared in the denominator. I'm just going to use this fact, but like I said, this relies on either the chain rule, seeing this as a composition of the original function f with the reciprocal function, or you can see it as, you can use the quotient rule, seeing this as the quotient of 1 and my function f. Okay, regardless, this is going to be, I take the derivative of cosine, which is negative sine of x, and divide by cosine of x squared. Now, why is this negative? This is the wrong answer. Why is it giving me the wrong answer? Okay. My mistake. See, I went and quoted a rule without actually remembering it correctly. Let me do this as a chain rule. This is the same as the derivative of f of x to the negative first power. So this is negative f of x to the negative second power times the derivative f of x. Okay, which is negative, this f of x to the negative second power means f of x to the second power is in the denominator, and the derivative of f of x is f prime of x. So I missed a negative sign in my remembering of my formula. Good lesson on me. However, the reason I knew that I had a mistake there is because I actually have, I remember what the derivative is of secant, and it was not consistent with that. So what do I need to do? This secant is 1 over cosine, and so that means I need to take the negative of the derivative of cosine in the numerator and then the square of cosine in the denominator. So that actually gives me, this is sine of x, Those two negatives cancel out and make a positive. Sine of x over cosine squared of x. And one way that we can actually make this into, I mean, we could leave it this way, but another way that we could make this kind of a clean presentation of functions, and the way that is most often presented, is I take one of the cosines to put with a sine, like that, and then I also have the 1 over an extra cosine in the denominator. Okay, so we have sine x in the numerator and two factors of cosine in the denominator. And so this is tangent of x, sine x over cosine x, and then 1 over cosine of x is secant of x. Okay, so there you have it. Derivative of secant is, and I often hear it quoted as secant times tangent. So derivative of secant x is secant x times tangent of x. So there you have it. Like I encouraged you with calculating the derivative of cotangent, similar to how we calculated the derivative of tangent, I also encourage you to calculate the derivative of cosecant, similar to how we calculated the derivative of secant. Okay, I am going to put them here, all of the derivatives of the trig functions, and I'm going to let you know what one way to economize remembering. So we have the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative of sine of x. The derivative of tangent of x is secant squared of x, and the derivative of cotangent of x is, I'm going to leave that for a minute, the derivative of secant of x is secant of x times tangent of x, and the derivative of cosecant of x is, I'm going to leave that for a minute. I highly recommend that you memorize the derivative of sine and derivative of cosine, okay? And I highly recommend that you remember how to get the derivatives of all of these other functions by writing those functions as combinations of sines and cosines. But it's also a good idea to practice just memorizing all of these derivatives, okay? They are all very related, and I can tell you, if you remember the derivatives of sine, tangent, and secant, then the derivatives of their co-functions, cosine and cotangent and cosecant, are basically the cos of the derivatives of the original with a negative sign. Okay? So the derivative of cotangent is the negative of the co of the derivative of secant. So it is negative cosecant squared of x. The derivative of cosecant is the negative of the cos of the derivative of secant. So it's negative cosecant of x and times cotangent of x. Okay? So I do recommend that you practice actually calculating the derivative of cotangent and cosecant and even tangent and secant based on writing those functions as combinations of sines and cosines and using the quotient rule or the chain rule. But also it is a good idea to at some point memorize these things so that they are more familiar, like ready in your brain when you need them. And this is a way to economize in remembering it. Remember all three of these, and then the derivatives of the cos are the negative of the cos of the derivatives of the originals. All right, good luck.